So there are three key properties that we think about when we're talking about relations. And before we jump in here to the reflexive one, the first thing I want to point out to you is that when we're talking about these properties, we're generally going to be talking about relations from a set to itself. Right? So you see that here in the first sentence. It says, let R be a relationship on a set A. You remember that's kind of a shorthand that we use when both the domain and the codomain of the relation are the same, right? So it's going to be A in both cases. So we say a relation has this reflexive property if and only if for every X in A is related to itself. Right, and just a quick example. I'll look at a quick example of each of these properties. Then we'll look at some more detailed ones in the next lecture. Suppose we have a relation where we say X is related to Y if and only if X is equal to Y. Right? This relation would be reflexive because if you pick, sorry, I should have defined a domain here, right? So let's say A is the set of real numbers. Right, so with this, to check this, right, if you pick any real number, that number is equal to itself, and that's what the relation requires here, right? So for every X, an element of the real numbers, X is equal to X, therefore X is related to X by this relation. So our second property here is what's called the symmetric property, right? And what this one says is if we take any two elements out of the set, and we know that X is related to Y, then Y also has to be related to X, right? In other words, the order that we look at the things in the relation doesn't matter, right? And again, just kind of a quick example of this. Let's say A is the set of integers, and let's say X is related to Y if and only if X and Y have the same parity. Remember, parity just refers to whether or not the number is odd or even. So hopefully this is pretty clear then, right? If X is related to Y, then X and Y have the same parity. But and now in the English sentence here, the order doesn't matter, right? So this is the same as Y and X have the same parity, which is the same, which implies Y is related to X as well. And that's what we need for this symmetric property. All right, so finally, third one here, we have this transitive property, and we've seen transitive properties before, right? It's the same thing here. We're going to start off with three elements of the set this time. And what the transitive property says is if X is related to Y and Y is related to Z, then we can kind of skip that middleman and just say X is related to Z. Right, and again, just a quick example of this. If A is the set of real numbers and X is related to Y, is taken to mean X is less than or equal to Y, then this transitive property is going to hold because we know that inequality for numbers is transitive. So again, if you wanted to kind of write this out, we would start by saying assume X is related to Y and Y is related to Z. But by the definition of my relation, this means X is less than or equal to Y and Y is less than or equal to Z. By the transitive property of numbers, this means X is less than or equal to Z. And again, now we fall back on our definition. This tells us X is related to Z. Right, so there you go. The transitive property applies to this particular relation. Okay, now we've got these definitions in hand, and I've run through a couple of basic examples, right? Kind of give you a feel for how we're going to prove each one of these for a given relation. So in the next lecture, we're going to kind of follow the same pattern we've been following here. We're going to look at some more interesting examples and kind of look at all three properties for a given relation. What we're really kind of looking for, looking ahead just a little bit here, we're really going to be interested in relations that have all three of them.